Welcome, mathophiles. On this adventure in algebra, we begin our introduction to group theory. So, here is our agenda. First, I'm going to give the definition of a group and some motivation for studying it. Then there will be a series of videos going over examples of groups along with proofs. And then there will be some videos going over properties of groups. And so the rest of this video will mainly be concerned with the mission 1, the definition and motivation. So here it is, the topic of your nightmares for the next several weeks, a group. A group is just a set G with a multiplication, which is a function from the Cartesian product of the group with itself to the group. In other words, given two ordered pairs, you get a new element in the set. So for any pairs G, H, you have some sort of x of G of H. Naturally, this notation is very cumbersome, and because the notion of multiplication and addition precede the notion of set and function, we're going to obviously use the notation we're more used to. So we're not going to write stuff down this way, we're going to write it using dot, or plus, or asterisk, or whatever operation we want. In other words, these are called binary operators. We're going to write G something H to represent a function on ordered pairs. So some textbooks involve an axiom for closure, although ours does not, and I usually do not. What it means that this multiplication operation is a function is that for every ordered pair, every pair of elements in your set, this product, whatever it is also an element in your set. So in other words, you have some sort of rule for how to multiply two elements to give you a new one. Of course, modern mathematics is all about definitions that have axioms. So here's our structure, and here are the properties we're going to require. The first property we require is called associativity. For any three elements in our set, if you take this triple product, these two different ways, you get the same result. So the first way says you multiply the first two terms together and then multiply by the third. And the second calculation says you take the first term and multiply it by the product of the latter two. So you see how these are slightly different calculations. And so the point is, for every three elements in your set, these two triple products are always going to give you the same result. And it's worth pointing out, in vector calculus, you will see a non-example called the cross product in R3. So the cross product in R3 is not associative, which is kind of weird, but hey, sometimes these things exist. And non-associative things are really terrible. So we like associativity. It's one of the things we like to work with. The main reason why is because then you can sort of ignore parentheses because they don't matter. The next property we require is that there's a multiplicative identity. In other words, there exists some element in your sets. For historical reasons, this element is always denoted E. And it has the property that for every other element, G, when you multiply by E, you get the element back. So in other words, E sort of plays the same role for this group G that 1 plays for the integers with respect to multiplication, or 0 plays for the integers with respect to addition, or the identity matrix plays for matrices with respect to multiplication. And so there you see the reason why we use this notation is because in various contexts, the identity element is denoted either 1, 0, or capital I. And so generically, we're always just going to use the little e for it instead. Please note, obvious disclaimer, in this context, this is not the natural number from calculus. The final property that we require in order to be a group is existence of multiplicative inverses. For every element in your set, every element little g, there exists some other element we're going to call g to the negative 1 that has the property that when you multiply g times g to the negative 1, you get e. So here order is important. 3 doesn't make sense unless you have a multiplicative identity, because it's used in the definition. So the point is you can multiply in such a way that parentheses don't actually matter. You have some sort of element that when you multiply by it, it's almost as if you're not multiplying at all. And there's some sort of notion of division. You can undo certain multiplications. And this is the definition of a group. Whenever you're asked to show something as a group, these are the 3 properties you have to check. Notice this is a universal quantifier over 3 elements. So any proof would involve taking any 3 elements and showing this identity is true. And this is an existential quantifier, universal quantifier, existential quantifier. Order of quantifiers matters here. You have to find this identity first. It holds for every element g. Here, this formula, whatever you use to define g inverse, is allowed to depend on g. So that's actually going to turn out to be very useful. I will add in the disclaimer that if you check the textbook, you will notice that their identity definitions are slightly different. They also require for multiplicative identity that you get this equation on the right-hand side too, that when you multiply little g by e on the left, you also get g. And then when you multiply g on the left by g inverse, you get e. We will see when we cover properties of groups that whenever the properties we had are satisfied, you actually can prove these 2 conditions are guaranteed to hold. And the reason why I say that is that means that even though this is the traditional definition of a group, it suffices to only check the axioms I had on the previous slide, because these other 2 axioms, these other 2 properties automatically hold for free. You don't have to check them. And so that makes some of the proofs go a lot quicker. Of course, there are some instances in this course where we need something slightly weaker. If you don't have inverses, but you have an identity on both the left and the right, and you have associativity, the structure you have is called a monoid. Yeah, it's a silly name, mono for 1, because you have 1 operation. This notion will arise a few times in this course, but it's not quite as important as the group one. So I would focus on memorizing the definition of a group and its 3 axioms. So what is the motivation for group theory? Well, I'll give some attempt to give the original motivation, but at some point we will get lost and I'll switch to something more modern and easier to understand. But we'll start a little basic. Suppose I have a polynomial, ax squared plus bx plus c equals 0. A, b, and c are real numbers. Then what is x? That's right, we all know the quadratic formula. X is negative b plus or minus the square root of b squared minus 4ac all over 2a. Now here's a harder one you probably don't know. Let's replace square with a cube. If x cubed plus px plus q equals 0, then what is the value of x? It turns out if you have an arbitrary cubic, it's possible to get it into this form by doing various substitutions, so this is actually the important one to be able to solve. Congratulations, here's the formula, in case you've never seen it before. This goes back to Cardano in the Middle Ages. It's kind of an interesting formula. So you do see cubed roots, you do see square roots. You see plus and minus here underneath this cubed root radical in both cases. And here the q's are the constant terms and the p are the linear terms. And out in front you have this weird thing, which is the cubed root of 1. It turns out, and here n is either 0, 1, or 2. So this tells you there's 3 different roots. And so this gives you the 3 roots to this polynomial equation. Now before I move on, I will note there's this nice symmetry here that if you replace plus with minus, that just swaps these two terms in this formula. There's also another symmetry that goes on where if you multiply by a root of unit, the cubed root of unity, this number right here, you're permuting the 3 roots among themselves. So we're not at the point in the course yet where we can talk about permutation groups, but basically at some point, after the course is over, if you go back and look at this video, you will discover that there's a symmetry group going on with the roots. Now we get to the harder example. How about an arbitrary quartic? Turns out this is really hard, so I'm not going to describe how to solve it, but it is in fact solvable, and it's been known how to solve it for centuries. There's various procedures. There isn't a nice one-line formula. The simplest formulas take, I think, 4 lines or so. But obviously it's a lot more complicated than the cubic. And then we get to the quintic, which means degree 5. So here's a polynomial of degree 5. Can you solve it? By which, of course, I mean like the formula we had for the quadratic and the formula we had for the cubic. And that was an open problem for centuries, and it eventually turned out and was proven that this isn't possible. And I should contrast, there's a difference here between really hard and impossible. I don't mean impossible like, it's not possible for me to become a millionaire, because theoretically that's possible by, playing the lottery and getting really, really lucky. Just highly unlikely. Here, impossible means there's actually a proof that there does not exist a formula where involving A, B, C, D, E, and F that if you plug the values in, it gives you the roots. And of course, there the definition of formula is complicated. It means basically what you think it might mean, the types of expressions we are already seeing, stuff involving square roots, cube roots, fourth roots, fifth roots, and so on. What does that have to do with group theory? Well, Galois was one of the people who proved this result. It was independently proven by Abel and Ruffini about the same time. And Galois' proof consisted of studying the roots of a polynomial equation. Like I had already noticed with the cubit, there are these nice symmetries of the roots. And so Galois decided to study symmetries of the roots of an arbitrary polynomial. And his main idea was that the symmetries of the roots actually had the structure of a group. And he showed that the solvability of this polynomial could be proven using these symmetries. In other words, whether or not the polynomial was solvable was based on whether or not these symmetries had some other property, which oddly enough is now called solvability of the group, which is kind of silly, but well, that's just the way mathematics sometimes works. And so he then showed that some of these quintics had unsolvable symmetry groups, and that completed the proof. And I think he was about 20 at the time, so yeah, what have you been doing with your life? My defense, I also did not prove anything that outlandish at the age of 20, so we're all in the same boat in that regard. So the point is, Galois invented group theory to study this problem, so that he could study symmetries of roots. And so that was the original motivation of group theory. It was to study symmetries of roots of polynomial equations. But of course, in order to actually understand that, you actually have to take modern algebra 2 all the way through to the end. So let's look at some applications that don't require another math course. So, molecular chemistry. is an example of an area of science where group theory pops up an awful lot. So I mean, what are the differences between H2O versus CO2 versus DNA? Well, DNA is a much more complicated structure. Now so H2O versus CO2, if you look at the diagrams of molecules, you'll notice that H2O has this bend in it and CO2 does not. And some of the chemical reactions are based on this fact that they're geometrically different. The DNA one's actually kind of interesting because historically the way they actually figured out the shape of DNA was by looking at the data set and looking for symmetries. And by looking at the symmetries, they discovered the rotational symmetry that allowed them to realize that it must be a double helix instead of, a straight ladder. So I can't draw the double helix because I'm not that smart. But a straight ladder has a different set of symmetries than the double helix shape, because the straight ladder, the only symmetry involves doing a 180-degree rotation, whereas the helix, if you rotate and move down at the same time, you will get the same picture. And so by doing that, they discovered that DNA must have this shape and not that shape. So they ended up looking at symmetries to discover what the shape was in space. Of course, to point that out, let's go back to these two simpler examples. What are the actual symmetries of these molecules? Well, it turns out there's about 4 symmetries of a water molecule. You've got a 180-degree rotation that fixes this vertex and swaps the 2 hydrogen atoms. You've got the identity symmetry that just leaves everything alone. That one's kind of weird, but we get used to the idea that that exists. And then, oddly enough, we have to remember that there's a 3-dimensional space that we're working in. There's this flat plane this molecule is sitting inside. These are viewed as 3-dimensional balls. There's this mirror basically going through the middle of the molecule. And that's technically a symmetry. The top of the ball is mirrored by the bottom of the ball on each of these molecules. And there's also another 2-dimensional vertical mirror going through the middle of that atom. And so there ends up being 4 symmetries. On the other hand, CO2 has infinitely many, because any possible rotation here gives a different symmetry of the molecule. In fact, actually, you can pretend that it's a toilet paper roll or a cylinder, and it's the same symmetry group. And so, graduate students in chemistry actually have to study this stuff. They study group theory, the same stuff we're studying, so that they can study symmetry groups of molecules, so that they can understand how that affects chemical reactions. Another application that's a bit beyond the scope of this course is to particle physics. So at some point, people were looking at fundamental particles like protons and electrons and the gluons that make up protons and neutrons. And they're looking at different characteristics like the spin. And they started realizing there was a relationship between these things and certain collections of matrices called matrix groups. And so then physicists conjectured that every matrix group must correspond to a fundamental particle. So this allowed them to conjecture the existence of fundamental particles we didn't know existed yet, and eventually they turned out to be right. And so all the fundamental particles correspond to matrix groups, and a lot of their physical attributes can be computed using group theory, which is, well, I'll admit, a bit mind-blowing. Other 2 areas of application are to cryptography. So that's the area of math that involves encoding secret messages or your bank account information on your debit card. And so there's a lot of group theory there. And there's also in an area of math called geometry, particularly algebraic topology and algebraic geometry. So here to geometric object, you somehow create some sort of group structure that tells you information about the geometric space. And I kid you not, this is the only way we know how to prove that a donut and a soccer ball are geometrically different up to some notion of geometry. Admittedly, that's about the most I'm going to spend with modern applications or motivations for the subject. Most of the time is going to be spent looking at examples because, well, at the end of the day, we got to learn the material. So it is worth pointing out one thing you might have noticed is that we didn't talk about commutativity. Commutativity is not one of the axioms of a group, but we can say it's a property a group might have. So if a group has this property, that is, for every pair of elements g times h is equal to h times g, then we say that group is abelian. In case you wanted to know, and because I've had students note that they didn't realize this before, that's actually named after someone, Abel, who was also someone who proved that the quintic was unsolvable. It's named so because when he studied groups, these were the only types of groups he considered. This is the same Abel that the Abel Prize is named after, which is a famous $1 million mathematical prize given out every year. And to end this video, I'll point out some other notes, is that sometimes for groups, we'll use addition and negatives instead of multiplication and inverses. So instead of using g times h and g inverse, we might use g plus h and negative g. And it is important that you have to be able to translate between these two for certain proofs, including the axioms. So, what would associativity look like? It would look like g plus h plus k equals g plus h plus k. And the identity would be g plus negative g equals e. The point is, we had these axioms, and I stated them in terms of multiplication, but you do need to be able to state them with regards to any type of group operation. And if I write things additively, you have to use negation instead of inverses. This is actually very important because some groups are written additively, and if you screw up this mix-up, you will accidentally be writing this instead of that. And if you do that, if you make this mistake in the middle of a proof, you could go off the rails and suddenly be claiming that 1/2 is an integer, which doesn't get you very far. Another disclaimer that pops up very quickly is that we will often use the symbol G to represent a group. I say this as a shorthand because the point is that technically G is a set. Our definition of a group is that it was a set equipped with a function called multiplication. But oftentimes in the notation, we will just write let G be a group, and it's understood from context that times is the multiplication, except if I say additive group, in which case plus is the binary operation. Finally, after having taught this course enough times, it is important to note we write G inverse for the multiplicative inverse. We do not write 1 over G. The reason why is because 1 over G is technically assuming commutativity. I mean, if you write f over G, do you mean f times 1 over G? Or do you mean 1 over G times f? Which is it? These are not the same thing. If you have a commutative group, then they are abelian group. These are the same thing, and there's no confusion. But if you're in a non-abelian group, there is a difference. If you go back to linear algebra, you never wrote capital A divided by capital B, where capital A and capital B were two matrices, and this is the reason why, because it's not clear what that means. You always wrote capital A times capital B inverse, and that is the convention we're always going to use in this course.